Okay, so suppose we have a graph G, which is a set of vertices V and a set of edges E. And the number of vertices, so the size of the vertex set V is equal to n. So there are n vertices. And we want to know what is the maximum number of edges that this graph could have. So if it has n vertices, how many edges could it have? We're going to figure out what that is. And this is typically one of the first things you learn in a graph theory course. And they might tell you, you might see the theorem in the book, the size of E is less than or equal to the size of V times the size of V minus 1, so the number of vertices times the number of vertices minus 1, divided by 2. If we have assigned this natural number n to the size of the vertex set, the number of vertices, then we can write this as n times n minus 1 divided by 2. And this might look familiar to you. This might be reminiscent of another formula we've seen, n times n plus 1 over 2. And of course, this is 1 plus 2 all the way through n. This is the sum of the first n natural numbers. And if that's unfamiliar to you, please do take a look at the video on that, because it's a pretty important sort of little thing to know. And there's a very nice little proof of this by Gauss, which he was supposed to have discovered as a child, and then another one using induction. And we're also going to do two proofs of this. The first proof that we're going to do of this fact is that is going to just sort of count the number of vertices if we try to make the number of edges using these vertices, using the vertex set. We'll call it V is equal to V1, V2 all the way through Vn. So we're going to say we have these n vertices, V1, V2 all the way through Vn, and we're going to try to think about how to construct a graph with the maximal number of edges. So connecting each one of these to as many of the others as we can, while not double counting, while not counting the same edge twice. So connecting V1 to V2 and then V2 to V1 and counting that, double counting that, because that's just one edge, right? We don't consider that to be two edges connecting one vertex to another. We're just going to consider that to be one edge. So let's think about this. Let's go one by one. We'll think about V1. And how many edges can we make using V1? So how many of these can we connect it to? Well, we can connect it to V2, we can connect it to V3, each time we do this we make an edge, all the way through Vn, we can connect it to Vn, so there are n minus 1 edges that we can make using V1 by connecting it to all the other vertices, V2 through Vn. And then we think about V2. How many edges could we get using V2? Well, we've already connected it to V1, so we're not going to count that one. But we could connect it to V3 all the way through Vn. We could connect it to those vertices and make new edges. And how many edges would we make if we did that? Well, now it's connecting to all of these n vertices, except for V1 and V2. So there's going to be n minus 2. We'll say new edges that we can make. So not double counting the edge that we made by connecting V1 to V2. And then we keep going like this. V3 is going to give us n minus 3 new edges, etc. And we're going to keep going down like this until we get to Vn minus 1. And when we've gotten to Vn minus 1, so the one right here, the only one that it hasn't been connected to so far is, I think, Vn, right? We haven't connected it to Vn, so we can get one new edge by connecting Vn minus 1 to V1. And so and then we're going to add these up, right? This is the number of edges that we were able to make. How many have we made? We've made n minus 1 plus n minus 2 all the way through, I don't know, I'm putting brackets here, we don't need brackets anymore, 2, plus the last one is 1, right? So Vn minus 2 would give us 2, which is, of course, n. So this one was n minus 1, this one was n minus 2, this was n minus 3. So the number of edges that you get from each vertex in the set, proceeding in this way, is n minus the vertex number. So this one gives us 2, which is n minus 2. Same thing with 1 is n minus 1. And so, well, that like triple highlighted. There we go. We don't want to double highlight either. We're gonna single count and also single highlight. There we go. N minus 1, n minus 2, all the way through to 1. And how many is this in total? Well, using our formula for the sum of the first n natural numbers, 1 plus 2 all the way through n, is n times n plus 1 over 2. Well, applying that with instead of the n here, instead of the n, we have n minus 1. Well, this is going to be equal to n minus 1 times n minus 1 plus 1 over 2. So putting the n minus 1 in the place where the n would have gone when we were adding up the first n natural numbers. And n minus 1 plus 1 is, of course, n. So this is n minus 1 times n over 2. And so that is one way to prove it. That's a very nice sort of clean, simple way to prove it. We'll see another way to prove it, because why not? Only deepens our understanding. In the next video, we're going to look at how to prove this by induction. So we're going to show that it's true for a graph with one vertex or maybe two vertices. You can do it for the base case. It doesn't really matter. The key is going to be the induction step. If we assume that any graph with, say, n vertices has at most n times n minus 1 over 2 edges, then we'll prove that a graph with n plus 1 vertices is going to have at most n plus 1 times n over 2 edges. And that'll be a very nice illustration of proof by induction, which we did earlier in the course. Never hurts to practice the basics.